According to some theories, during the collision process, particles could momentarily travel into the hidden dimensions, carrying energy and momentum away from our observable three-dimensional space. These escaping particles would leave behind a deficit in energy and momentum, giving the impression of a violation of conservation laws. Experimental observations at CERN have hinted at such energy and momentum imbalances. The detection of missing energy or momentum in collision events, which cannot be accounted for by the known particles in the Standard Model, suggests the possibility of interactions with particles residing in extra dimensions. By carefully analyzing these missing energy and momentum signatures, scientists can investigate the potential influence of hidden dimensions on the conservation laws. While the observations of energy and momentum conservation violations are intriguing, it is important to note that these violations are not definitive evidence for the existence of extra dimensions. Alternative explanations, such as undetected particles or systematic errors, must also be considered and thoroughly investigated. However, the persistence of these anomalies in experimental data and their compatibility with theoretical frameworks encourage further exploration of the dimensional hypothesis. Number 9. String theory predictions and CERN. String theory, a theoretical framework aiming to unify all the fundamental forces of nature, has garnered significant attention in the search for a deeper understanding of the universe. In this chapter, we explore the predictions of string theory and its implications for experiments conducted at CERN. One of the fundamental tenets of string theory is the notion that elementary particles are not point-like entities, but rather tiny, vibrating strings. These strings oscillate in different modes, giving rise to a spectrum of particles with various properties. String theory also posits the existence of extra dimensions, often 6 or 7 in total, which are curled up at scales much smaller than those accessible to current experiments. String theory predicts that the energies reached at CERN's LHC may be within the realm where the effects of extra dimensions become apparent. These extra dimensions can manifest in various ways, such as modifying the behavior of known particles, introducing new particles associated with the extra dimensions, or altering the strength of fundamental forces. By carefully studying the collision data at CERN, scientists can search for signatures that align with the predictions of string theory. One prediction of string theory is the presence of additional particles known as string excitations, or string states. These particles, associated with the vibrations and modes of the fundamental strings, could have distinct properties that differ from those predicted by the Standard Model. By analyzing the collision events and studying the properties of the produced particles, researchers at CERN aim to identify potential string states and probe their connection to the extra dimensions predicted by string theory. While string theory has yet to yield definitive experimental evidence, the predictions it offers provide a rich framework for exploring the nature of the universe. The continued investigation of string theory at CERN and other research institutions contributes to our understanding of the potential existence of extra dimensions and their implications for fundamental physics. Number 10. The influence of the many worlds interpretation. The many worlds interpretation, MWI, is a theoretical framework in quantum mechanics that proposes the existence of parallel universes branching out from every quantum measurement. In this final chapter, we explore the influence of the MWI on our understanding of the dimensional hypothesis and its potential connection to the experiments conducted at CERN. According to the MWI, when a quantum measurement is made, the universe splits into multiple branches, each representing a different outcome of the measurement. This interpretation offers a radical perspective on the nature of reality, suggesting that an infinite number of parallel universes exist, each with a slightly different configuration of particles and forces. These parallel universes could potentially be associated with other dimensions beyond our observable reality. The MWI has significant implications for the dimensional hypothesis. If other dimensions exist, they could be manifested as distinct branches of the multiverse within the MWI framework. Each branch could correspond to a different configuration of extra dimensions, potentially explaining the variations in the fundamental constants and laws of physics observed in our universe. Furthermore, the MWI can shed light on the concept of wave-particle duality and the behavior of particles in the context of extra dimensions. In the MWI, particles are not confined to a specific classical trajectory, but exist as a superposition of different states. These superpositions can extend into extra dimensions, leading to the possibility of particles simultaneously existing in different dimensions, or branching out into parallel universes. While the MWI is a controversial interpretation of quantum mechanics, its influence on the dimensional hypothesis offers a fresh perspective on the nature of our reality. The potential connection between the MWI and extra dimensions opens up new avenues for exploration at CERN, where experiments and observations can provide insights into the existence of hidden dimensions and their manifestation as branches within the multiverse. It is important to note that the MWI is still a subject of ongoing debate and research, and its empirical validation remains a challenge. However, the influence of the MWI on our understanding of the dimensional hypothesis underscores the significance of considering alternative interpretations and their potential implications for experimental investigations.